Bien, bonsoir à toutes et à tous. Je vais parler en anglais pour présenter notre conférencier. So it's a real pleasure to have Wilhelm Zwerger with us today. I think most of you know Willy. You may not know what everything he has done in his life. Willy is like the Egyptian cat, who they have 9 lives. So Willy has had probably more than 9 scientific lives in his career. He has touched many subjects with very successful results. I will not tell you everything, but I would like to say a few words. Just maybe I could take this microphone with me. Well, like this, okay. I will not tell you everything, but just a few steps in his career. He started with a PhD in surface science some years ago now. And then it was around 81, 82. And then at that time, as many of us, he was fascinated by the 2 papers by Caldera and Leggett about macroscopic quantum tunneling and the role of dissipation and coherence in quantum many-body physics. And then he turned to this subject, first in Hamburg as a postdoc, and then directly with Tony Leggett. You were very fortunate to spend some years there. And then he decided to go to something else. So I think you have worked on Josephson junction arrays. In around 1990, you worked on the BEC-BCS crossover, well before any people in cold gases could think that one day this would be relevant for atomic gases. But at that time, it was the time of high TC superconductivity. So, this crossover between Bose-Einstein Condensation and BCS could be a solution to the high TC problem. Then Willy was interested in still another topic. It was the time of mesoscopic physics, and so Willy has worked on these problems experimentally in France. There was the group of Michel Dévoré and Daniel Estève were doing this mesoscopic physics, this single electron box, and Willy has made very important contribution to this subject. And then we arrive at the time of around 2000, maybe slightly before, where there you met the group of around Ted Hensch, Tilman Esslinger, Emmanuel Bloch. And then you decided to go to cold atomic gases with the success that we all know. And Willy has made many seminal contributions for atomic gases. There again, the BCS-BC crossover, but from the atomic point of view. Also the superfluid to mode insulating transition and many other things. And in parallel, you also worked in nanomechanics and optomechanics. You have also, during these last 10 to 20 years, made very important contribution to that. As a personal note, I would like to add that I had the chance to write a review paper with Willy, a paper that you may know. And for me, it was really a fascinating moment. It took us 2 or 3 years to write. But Willy is really a living encyclopedia. And I learned a lot simply by discussing with Willy, asking him to explain me why we had written this in the paper, essentially. Okay, so it's really a big pleasure to have Willy with us. I will end by saying that Willy has held a faculty position in many places, in Göttingen, in Munich LMU, in Innsbruck, and then in TU Munich, where you are still now. He has been a visiting professor at Illinois, I already mentioned this, at ETH Zurich, at MIT Harvard, in Trento, in Lausanne, and now with us for 4 weeks and with 4 lectures, and this is today the first lecture. So I'm really very happy to give the floor to Willy. Before that, there is a formality, which is a very pleasant one. I have to give him a medal, and here we give the medal at the first lecture, not at the last one. So I have to give him the medal of Collège de France of the visiting professors. So here is the medal, Willy, assuming that you will.
Merci beaucoup. Okay.
Okay, the floor is yours.
Okay, yeah. Dear Jean, ladies and gentlemen, it's of course, first of all, I want to thank Jean for the invitation to come here. It's a big honor to be at Collège de France for an extended time, which I've never been so far. I've been in Paris a number of times, but never sort of for a longer period. And for me, in a way, preparing these lectures and also the lecture notes, which you will find online, in a way, is a tribute to the deep appreciation I've held for physics in France, for the physics community in France, for a long time. Actually, this appreciation goes back around 30 years to, as Jean has mentioned, my connections to the group Contronic in Saclay, led by Michel Devoré and Daniel Esdev. Then actually sort of my discovery of the textbook of Roger Ballion on From Microphysics to Macrophysics, which actually has formed the basis of my teaching of statistical physics and thermodynamics throughout my career. A visit in Grenoble with Philippe Nozière, where Nozière explained a few things to me, or mentioned a few things to me I never had heard of. And actually, during the talk today, I will actually mention and expand upon some of those things which Nozière at that time in the late 90s explained to me. And then, as Jean mentioned, when I switched in the late 90s, around 2000, to ultracold atoms, of course, I had a wonderful French postdoc, Jean-Noël Fuchs, who worked with me in Innsbruck, having been done his PhD with Frank Laloué. Then, as Jean has mentioned, the 2-year or even longer, 2.5 years or so of writing the review of modern physics, where, okay, both Emmanuel and me, I think, had the privilege to work with you, and I think we learned a lot from each other, clearly. And then in my work on the BCS-BEC crossover, of course, there's long-standing interactions with the groups here, experimentally, Christophe Salomon, Frédéric Chivy, on the theory side, Yvon Castin, with Felix Werner, who is here. And also, I should mention Jora Shlapnikov and Dmitry Petrov, who has sort of, in a way, introduced me to the field of few-body physics, which I think I also had some interest in. This list is not complete, but it shows that it indicates I have sort of I've profited a lot from interactions with the French community, and of course I'm happy sort of that this is still ongoing. Okay, so the topic of these lectures overall is Bose-Einstein condensation and superfluidity, and of course the field has been started by Einstein almost 100 years ago. There were fundamental contributions by Landau, Bogoliubov, Feynman, Onsager, Penrose, many people, many years, many decades ago. And so you might ask, I mean, is this field still sort of interesting to be discussed today? Now, of course, one answer is, okay, we now have ultracold gases, and they have opened a new perspective in this field. And I think this is certainly a good argument. But I think it's not the full truth. The full truth is that, and this is something that I hope to show in these lectures, that the appearance of ultracold gases in particular has led us to revisit old problems and get new insights into those problems that in a way could have been asked many, many years ago, but haven't been. And I think there's many things that have been now only understood with ultracold atoms, although these systems are in a way perhaps the simplest kind of examples for Bose-Einstein condensates and superfluids at all. In a way, this is an example. What I would say is that something that we all know, that, I mean, science is of course always moving, it's never static. I mean, and even in fields where it is thought that, okay, maybe we understand everything, it is important to keep on asking questions. It's never good to say, well, all is fine and we should not think more about this. And I think this point of, in a way, keeping on and asking questions and not believing things and taking for granted and, okay, just put it onto the shelf is captured very nicely in a few sentences in the preface to the 2-volume book by Claude Tixon and Jean-Michel Drouf. I hope I spell him reasonably correctly. Where they say a book, and here you can say these lectures or lecture notes, they might give the impression that some knowledge has become definitive and the authors understand every part of it and everything is closed. This is a completely false view. I mean, it's a very strong statement by someone like Claude Tixon. And he says, okay, no one, well, he phrases it in a personal manner, but I would phrase it more generally, sort of, a subject is never really closed, and this is, and thinking about and asking new questions is a source of progress. Okay, after these introductory remarks, let me start sort of with the topic of BEC and superfluidity, and in a way, jump into the deep water right away. Start with the definition of BEC in an interacting system that was given by Penrose 70 years ago. And if you have not seen this definition, it's a so-called off-diagonal long-range order. The one-particle density matrix at widely separated points approaches a constant. Then, this is pretty formal and not immediately sort of intuitive what it means. But what it means is, in a way, in the end, relatively basic. It's long-range phase coherence. Imagine sort of you take, it's long-range phase, it's long-range order in a property, not in some magnetization, as you can easily imagine, as in a ferromagnet, but in a field operator. But if you take the expectation value of this in a state with n particles, then acting with the field operator annihilation at x prime means just you take out one particle at x prime. If you pull the side dagger to the other side, you take the same state and pull out a particle not at x, but at x prime, but at x. And then you take these 2 points far away. A finite overlap of these two many-body states, that's BEC in a general way. So that's very intuitive. And in a way, this definition has been made concrete only with cold gases. Namely, in the year 2000, actually as part of the PhD thesis of Emanuel Bloch, they did essentially precisely that. Namely, they took a trapped BEC of rubidium-87 in a magnetic trap, so you have a harmonic confinement by the magnitude of the magnetic field in a certain hyperfine state, which is a weak field seeking state. And then you apply an RF frequency which flips the state into an untrapped configuration. And you have two different, and so this flipping appears at a certain height in this trap, because sort of the condition for resonance is dependent on the height, because the magnetic field depends on C. And if you have two different frequencies, this basically means you outcouple two beams of particles from this condensate at two different points. And then you look at the visibility of the interference fringe. And what you find here is shown on the right, is namely that this visibility, as a function of the distance, which you can change by changing the frequencies, approaches a constant sort of below Tc, which for this gas is around 400 nanokelvin, and goes quickly to 0 above Tc. And so, at least for this relatively simple system, and for these scales you see here, of course, you don't reach infinite separation. You reach a separation of a few interparticle spacing. But you see nicely this gives a nice signature of off-diagonal long-range order about 50 years after Penrose had proposed this. And there's no other system where, this has been able to realize. So it's a very basic and fundamental experiment. Now, this long-range phase coherence embodied in this off-diagonal long-range order is, of course, something which appears exotic. Long-range phase coherence, quantum mechanics at a macroscopic scale is not something that, you think is easy to reach. And of course, with these cold gases, you have to cool them to below microkelvin to reach it. And so you might ask, well, is this condition of Bose-Einstein condensation something super special? You have to do great efforts to, of course, cool it. You have to have perhaps almost no interactions as in the system. What about, I mean, for instance, increasing interactions? I mean, does it go away or something like that? And what I will show is that, and this is in a way the first part of the talk, half of the talk today, is no, not on the contrary. Bose-Einstein condensation is the generic ground state. You always get it unless the interactions can be as strong as you wish, unless you form a solid. Then things get more subtle, and those subtleties I will discuss in the next lecture. But as far as you have a uniform fluid phase, either a gas or a liquid, then they are always, the ground state is always a superfluid. So it's a generic ground state for bosons. And so this brings me to the outline of the lecture. So I will start with discussing BC in the presence not of, say, weak interactions as we had it sort of in this rubidium gas, but even in strong interactions as we have it in helium-4. And I will then also contrast the condition for BC with the condition for superfluidity. And basically the upshot of this discussion is that any fluid ground state of a Bose system is a BEC. It's very generic. And in the second half of the talk is then I will say, well, fluid can either be gas or liquid. The question is then, I mean, what decides whether it's a gas or a liquid? I mean, what separates that? This is a question actually raised in these old lecture notes by Nozier, and then I will show there are some new insights into that problem, and they are actually sort of also important to understand things that have been looked for a long time in Bose systems, namely sort of, do you have bound states of bosons not only for 2 or 3 particles, but I mean for many, 5 body bound states or something like that. Okay, so let me start with, in a way, cranking up the interactions, if you wish, and say, well, I mean, what happens if you have a strongly interacting Bose system? This was addressed seriously for the first time by Feynman in the 50s, in an influential paper by Feynman in 53, and Feynman had the brilliant idea to say, well, maybe knowing that the ground state of a Bose system can be chosen as real and positive everywhere, maybe I can write it as the square root of a classical probability distribution for classical n particles. For a harmonic oscillator, you can easily do it. You know, a harmonic oscillator ground state is a Gaussian. You just take the classical distribution of a single particle in an oscillator potential, choose an effective temperature, which is the 0-point energy, and then you have the ground state of the harmonic oscillator. Easy to do. So the question is, I mean, maybe you can do this for many particles, identical ones, symmetric in all the coordinates. And what this gives you is, of course, it reduces the problem from a quantum problem to a classical problem. Classical n-body problems are still not easy, but I mean they're much more simple, of course, than the classic, the quantum n-body problem. Okay, this was, as I said, introduced by Feynman in 53, and then was taken up by Onsager and Penrose in 56. Now, if you do this, and if you assume this, then you can say, well, let's check with this assumption whether we can produce, whether this system has BEC. Under which conditions does this ground state have BEC? So you have to calculate this one particle density matrix. So you have to know, I mean, in a way, extracting or adding 2 particles at widely separated points, does it go to a constant? In this classical system, you can actually do this easily, and sort of I've pictured this on the right-hand side. Basically, you can show is that this one particle density matrix can be expressed as a ratio of 2 expectation values in a classical n-1 particle state, where in the numerator you add 2 particles at point x or point x prime, but they interact with the rest of the particles only with half the strength of the other particles. That's in a way indicated by these 2 guys, which look like the half moon. And in the denominator, you just add a single particle, and if it's a fluid state, it doesn't matter where you add it, and you take the exponential average. Now, if you have a classical fluid with short-range interactions, adding two particles at widely separated points factorizes. Sure. And so basically, without doing much of a calculation, you see that this assumption of representing the many-body wave function in terms of a classical probability, n-bodied probability distribution, automatically forces you to a finite condensate fraction. You get even an explicit expression for condensate fraction where you have to calculate this exponential average of, in a way, adding one particle at any point in a homogeneous fluid, once with sort of the full interaction, once sort of the square of the one with the half interactions. Very simple. And so the conclusion is, from this simple exercises, any fluid ground state of a Bose system is a BEC. This point was not made in the paper by Feynman nor by Penrose and Onsager, but it's a consequence of what they assume. And also you don't find this expression there. So this is this so-called Widom particle insertion was invented by Ben Windham in the 60s in the theory of classical fluids. I just reformulated things in a way. So looks nice. And what I will show is that the conclusion is right, that the conclusion is correct, but the argument is fishy, is wrong. What's the problem? So what's wrong with Penrose Onsager? I mean, Feynman, to be honest, was clever enough not to draw this, not to go further as Penrose Onsager did. Penrose and Onsager in '56 said, well, they wanted to understand helium-4. They said, well, maybe we can treat helium-4 as a bunch of hard spheres. Not such a good approximation, but maybe try that. Then, half of the interaction is the same as the full interaction. And therefore, you see these ratios. So the numerator is just the same as the denominator. And since you have to square it, it cancels out. And what you get is the condensate fraction for a hard sphere gas, quantum hard sphere gas, is the classical exponential average of this additional work you do by adding one particle at some point in this fluid. And that's actually working out this expectation value is easy, it's actually an example of the Jaczynski equation. Hindsight is much easier than foresight. The Jaczynski equation was found in the 90s, late 90s. But actually, this is an example of the Jaczynski equation. Penrose and Onsager didn't know about this, but they realized that this ratio can be determined from the excess chemical potential of a classical hard sphere gas. Classical hard sphere gas, even in the 50s, was reasonably well known, well understood. And they used to say they know what the density of helium-4 is, and then in terms of the hard sphere diameter, and said, okay, the condensate fraction in this system, it will be a condensate, and it will have a condensate fraction of about 8%. Whew. It was fantastic. In '56, 30 years before people numerically could do this on analytical grounds. Unbelievable. But now comes sort of a bit of cold water. And this is the cold water which Nozier put on me in '99. He said, well, it's wrong. What's wrong? Well, let's try to say, well, we are not interested in helium-4. Let's try, we are interested in a dilute gas of bosons. And let's see what the prediction of this method is for the condensate fraction for a dilute system. And then, you just do a virial expansion for a classical gas. You get some effective virial coefficient B2 tilde. And the condensate fraction deviates from the ideal Bose gas, where it is, of course, in the ground state 1, by a term which is linear in density. And that's wrong. It contradicts Bogolyubov 47. So what's wrong? Well, what's wrong is that you cannot, it's impossible sort of to describe a quantum state, a quantum ground state in terms of a classical probability distribution, even if your sort of wave function is positive, definite, and so on. You cannot do it. And sort of a formal way to do it, to see it, is that a classical system at some finite effective temperature always has some sort of number fluctuations, or the static structure factor in the zero momentum limit is finite, while the compressible quantum system has a static structure factor which rises linear in momentum. That's not possible. So basically you cannot do this. It gives you fortuitously a prediction which is in the literature for now 70 years or so, but it's not completely kosher. Okay, good. Now you might say, well, perhaps, I mean, Bogolyubov wasn't right. Have we tested Bogolyubov? Now there's one person here in the audience who has tested it, namely, and not so long ago, Rafael Lopez, being as part of the group of Sora and Hatzibabic in Cambridge, 2017. They have, for potassium-39 in a box potential. You see sort of the box here, so it's a cylindrical blue system in the inset of this figure, 50 micron long, 25 micron radius or something like that. In this system, you have a momentum distribution where you have, in a way, a condensate peak, which is Fourier limited because of the finite length, and there's some depletion. And in a way, the depletion tells you how much has been kicked out of the condensate by interactions. This is an exaggerated picture by square root NA cubed around 0.2. In reality, it's not that large, but I mean, just to show the picture. And what they've done is use an idea which goes back to Fabrice Gerbier and Alain Aspect and Joseph Tyvison some time ago, two-photon Bragg scattering, where you coherently couple K and K plus Q, and actually you choose the frequency, sort of frequency difference in these two Bragg peaks as such as to basically you only couple out, or you couple K equals 0. So basically you are able to separate, spatially separate in the end with the momentum along C, the condensate from the non-condensate part. And you get a Rabi type oscillation, and sort of you see on the right figure, the displaced fraction as a function of the time taken in a picture after sort of 10 milliseconds. And they've used potassium-39 because this system has a nice Feschbacher resonance where you can change the scattering length. You cannot change the density too much, but you can change the scattering length. And then by changing the scattering length, they could, in a way, change this expansion parameter within Bogolyubov theory from in the range between 0.01 to 0.04. And then you get condensate fractions which are on the order of 95 to 90%. So you are already now pretty appreciable away from sort of the almost ideal BCs we have with rubidium-87, and you can check over the scale which is available to you, scattering lengths between sort of 700 and 3000 a Bohr. You can change what the Bogolyubov prediction. Now you can ask, I mean, do we have condensates now that in a way cover the full range, not only say near 1, but also, I mean, and near 90% to down to 0, almost 0? Well, we have. There is one example sort of which comes next. This is the unitary Fermi gas, where I've worked a lot on, and actually one of the experimentalists here on this paper sits in the audience. Kwon et al. This is a work by the Lenz group, Matteo Zoccanti, Giacomo Ruati, Francesco Scazza, Massimo Inguscio, where actually from the Josephson effect between two unitary Fermi gases, the critical Josephson current turns out to be proportional to the condensate density. It's a measure of the condensate density. And if you analyze this experiment, it's a completely different way of measuring condensate density, you can actually extract in agreement with the theoretical expectation is that the condensate density of this system is about 0.5. You can go even lower to unitary Bose gas. If you crank to infinite scattering for the Bose gas, that's not a very stable system, but there are some estimates again from Raphael and the group of Soran in Cambridge about 3 years ago, where they estimate the unitary Bose gas condensate fraction to be about 0.2, and then you can ask, well, maybe we can go even lower. Well, not perhaps with ultracold gases, but in a way with very mundane systems. You know, if you take aluminium as that's a Fermi superfluid. And you know, in a Fermi superfluid, this is described by BCS theory. Condensation, the pairing only is happening very close to the Fermi surface. There's a very tiny sheet where this happens. And the condensate fraction in this system, you can properly define the condensate fraction in this system, is of the order of Tc over Tf. So if you take the superfluids that you use sort of for the chosen quantum computer, the chosen in aluminum with aluminum junctions, the condensate fractions are 10 to the minus 3 or even smaller. So in a way you can say we have the full range. Okay. So far at the moment for BEC and condensate fraction, what about superfluidity? Now I've argued that BEC is defined by a overlap of many-body wave functions, long-range overlap of many-body wave functions. In a way, a similar thing happens for superfluidity, but in a different way. Namely, you have to essentially go to a rotating system. You take a fluid or superfluid, ideally in an annulus, and rotate it. The annulus has some sort of non-ideal shape that you can sort of, in a way, exchange angular momentum between the fluid and the boundaries. And if you go to the rotating frame, where sort of the boundary conditions are stationary, then in a way in this rotating frame there is no effective gauge field, but the fact that you're rotating is apparent from the fact that the many-body wave function in this geometry is no longer single-valued. Namely, if you go with one of the particles around the ring, L is 2 pi r, then you pick up a phase, e to the I or e to the minus I theta. And this theta is proportional to the angular rotation frequency. And therefore, in general, sort of the eigen energies, this is just like you take particle in a box, you go from periodic boundary conditions to anti-periodic boundary conditions, and then, of course, you change the energy. This change in energy gives rise to, even in thermodynamic sense, to a change in free energy, which depends on this variable theta. And as defined a long time ago by Byers and Yang in the context of their proof of flux quantization in rings, you can expand this out, and for a system with time reversal invariant interactions, it contains only the even Fourier components. And the question is, I mean, what are these FL? I mean, how is the system, in a way, sensitive to changes in the boundary conditions? That's, in a way, superfluidity. Microscopically, you can get this delta F and these Fourier coefficients from the winding number distribution. You have n particles. Each of these particles has an integer winding number around the ring, and so you have n winding numbers, and basically the characteristic function of this winding number distribution is giving you this free energy difference. This has been used by David Zeppeli later on in part integral Monte Carlo calculations of superfluid densities. Now, what distinguishes a superfluid in this system is that, okay, as you know, if you rotate a superfluid bucket very slowly, it doesn't rotate, it doesn't go with the walls. And this experiment was done with cold atoms here by Jean and Frédéric and Wohleben and Madison long time ago. And what you see here is the picture of the gas in C below the critical rotation, where there's no vortex in the system, and then a bit above it, where there is a single vortex there. And so this comes from the periodic dependence of this free energy difference as a function of this theta, and it has minima at sort of theta 0 to pi and so on. But the question is, of course, I mean, how deep are these minima? A constant function is also periodic, but I mean, then you don't have any flux, any of these quantizations. You need some sort of, in a way, appreciable barrier between these distinct, topologically distinct states. And this allows you, from the curvature around one of these minima, to define the superfluid fraction, which I call Fs in analogy to F0, the condensate fraction, from, in a way, the derivative of this parabolic function near the origin. And what this Fs means is this is, in a way, the fraction which does not rotate with the container for small angular velocities. And you see, I mean, if you're the rotating frame, not rotating with the container means sort of in the rotating frame, the fluid, in a way, goes counterclockwise. Goes clockwise. You have rotated counterclockwise, but goes counterclockwise. This is this minus here. And what this requires is that these Fourier components, scale with the system size in a specific way. Namely, there's a prefactor which defines the superfluid density. It must be scale linearly with the area, and they must go down very slowly only with the circumference of this ring. And this is something I will not be able to go into here in any details. In a famous paper by Leggett in the early 70s, he has shown that basically a finite rigidity here in this sense is obtained if the many-body wave function if you take one particle around the ring, you keep all the others fixed, and then you still have a finite value for of the wave function. If you have a fluid state, then basically this many-body wave function remains finite on closed parts with finite winding number. Then you get this finite superfluid density. And so this confirms my earlier statement that basically as long as it's fluid, the interactions may be as strong as you wish, it is a superfluid. Now, of course, you see the definition of superfluidity and Bose-Einstein condensation are very different. And you can ask, what is the precise interrelation between these two concepts? And okay, I don't want to enter that discussion because it can be endless. This is not what I really want. These two things are in a way two sides of the same coin. My own view is actually that superfluidity is the more general phenomenon. BC is sort of the descendant of that. That's not a generally accepted point of view. And I will not discuss this any further. What I might, if people are interested, I could, after the talk, give you a simple argument, which I actually learned from Mosier, about the thing which causes headaches to many people. Why can a system, or why is a system fully superfluid at 0 temperature, although the condensate fraction is maybe only 10%? That's not so immediately obvious, but there's a simple argument for why this is true, and I can, if people are interested, come back to this after the lecture. So in the second half of the lecture, I come back now, and I've, in a way, argued that whatever state you get, if it's a fluid state, the ground state has long-range order, long-range phase coherence. What distinguishes whether it's a gas or a liquid, and can we perhaps go from gas to liquid? That's, of course, the interrelated question. Now, quite generally, I suppose I ask or I discuss interactions, neutral particles with interactions which have some strong repulsion at short distances. The short distance scale I call sigma, and have some van der Waals tail at long distances, minus C6 over R to the 6. I don't care about the details of the interaction, but this is, of course, an interaction which we typically have in ultracold atoms, but you also have in helium-4. And the typical example would be the Leonard-Jones interaction, but that's not necessary for the arguments I take. Now, if you have this long-range van der Waals interactions, this immediately, besides sigma, defines a second length scale, namely the van der Waals length, which is defined in this way. So you just calculate at which distance is the 0-point energy at this scale equal to the interaction energy of the minus C6 over R to the 6th term. And if you fix C6, then you see that if I go to the classical limit, I formally let h bar go to 0, this van der Waals length is much larger than the short distance scale. This is the typical situation we, of course, have. And then we go to the classical limit. Now, if you have a classical system of particles with such a type of interaction, this is well known what the phase diagram is, the equilibrium phase diagram. And it's shown here on the right. In reduced units, you measure temperature in units of the depth of this attractive potential. You measure pressure in the characteristic units of pressure, which is energy density, so epsilon divided by sigma cubed. And in these units, then you get, by the law of corresponding states, a universal quote-unquote phase diagram, which of course depends a bit on the detail of the interactions, but not that sensitively. And lo and behold, of course, at low temperatures and high pressures, it's a solid, and then you get a liquid vapor, they get a triple and a critical point. This picture is taken, it's quantitative. You see it's taken from a French physicist working in the United States, Alex Traversé. And you say, well, 2014, I mean, did it take to 2014 to calculate this? No, not, but in a way, yes. What's the problem here? The problem here is not that what I will be concerned with, but what you see is the solid phase here has two phases, HCP and FCC. And evidently, FCC has a higher entropy because, I mean, this appears at finite temperature than at a given pressure. And it turns out the entropy difference between an FCC phase and an HCP phase in such a simple system is less than or of the order of 0.003 K-Boltzmann per particle. To resolve that, you have to do extremely good numerics, even for a classical system. That's pretty subtle. But of course, I mean, what interests us is, in a way, how can we add quantum mechanics to that picture, and how can we go now from a system which doesn't have a solid ground state to perhaps a liquid ground state or even a gaseous ground state? Evidently, the triple point or the critical point they have to approach to zero, and this is precisely how they do this. Was precisely a question that Nozière actually asked in his lecture notes at here in '83, so 38 years ago. I think it was the first lecture which Nozière gave at Collège de France, Liquide et solide quantique. And what he shows is, what he does, and you have one page out of his lecture notes, what he says, okay, let's just use the triple point here is in this dimensionless units at around 0.7, the critical point in temperature, the critical point is at 1.3. Let's just see about adding quantum mechanics to this picture. How do these points evolve? That's shown here on this hand-drawn figure by Nozière, and they go down, as you expect, by increasing the strength of the zero-point energy, which is measured by the de Boer parameter. The de Boer parameter in general is the square root of the ratio between the zero-point energy at the scale sigma divided by the epsilon. For these potentials with van der Waals interactions, it has a much more intuitive interpretation. It's essentially the square of the ratio sigma divided by L van der Waals. So if you have the typical situation where the short distance scale is much less than the van der Waals length, the de Boer parameter is very small, and now we crank it up. And so what Nozière shows, just empirically, both the triple point and the critical point go down continuously with increasing square of the de Boer parameter. And first the triple point hits zero, and then the critical point hits zero. And they do so, of course, now it depends on whether you have, I mean, your particles you're talking at are bosons or fermions. Turns out for bosons, this is the B here, the bosons, the triple point first goes to zero, and then for fermions. But then, in a way, for the vanishing of the critical point, it's the other way around. Well, actually, it's easy to understand. I mean, fermions don't like to see each other. They don't like to meet. What's the phase in nature where sort of particles continuously meet? Well, the liquid phase. In the solid, you can happily live solitary. You're not meeting anyone, classically speaking. In the gas also, it's very rare that you meet other guys. But in the liquid, you're always bumping into each other. And so fermions don't like that. And that's why the fermion part here in this picture is sort of small. Once the fermions go liquid, they try to get out of it as quickly, they evaporate again as quickly as possible. Okay, so now it turns out that the first transition where the triple point vanishes is the transition where sort of the ground state of the system is no longer a solid, but is a liquid. But this is a quantum phase transition. It arises at 0 temperature upon increasing the 0 point energy. It's a quantum phase transition, but it's a first order quantum phase transition. The position of this point is known numerically, was known already in the early 80s, but it's difficult. There's no easy calculation. That's a non-trivial problem to determine this point. What I will argue then is that, and then sort of in this intermediate regime, the ground state is a liquid. But then eventually, sort of, if you crack up the 0 point energy sufficiently far, the ground state is a gas, the ground state. What I will argue is that at least for bosons, for fermions, the problem is actually not solved. For bosons, the point where this critical point hits 0 temperature is actually determined by something very simple, two-body physics, just 0 scattering length, that's all. So it's extremely, I mean, to locate a quantum phase transition based on two-body physics is not that common. So how do I relate this? Well, I have to determine how is the de Boer parameter sort of that I crank up here, the 0 point energy, related to the scattering length. If I have a deep potentials with van der Waals lengths much larger than the short distance scale, I have many bound states. But you know, in quantum mechanics, attractive wells need a finite critical depth to bind to particle state. So if I make the depth smaller and smaller, there's a point where the last two-body bound state, S-wave two-body bound state, disappears. And this happens at sort of the unbinding value of the critical de Boer parameter for two particles, which turns out to be 0.42, or essentially a van der Waals length, which is only 9% larger than the short distance scale. It turns out that helium-4 is very close to this point. So if you plot the scattering length as a function of the de Boer parameter, we are now sitting, you see there is this pole here, the vertical dashed line, where there's a pole in the scattering length. Helium-4 sits a tiny bit to the left of this point. Has a positive scattering length, but has a two-body bound state. There's a helium-4 dimer that was discovered experimentally by Jan-Peter Tönnies in Göttingen in the 90s and measured out rather precisely. That's pretty tricky business because the binding energy is 10 to the minus 4 of the well depth. It's millikelvin binding energy. So helium-4 sits almost at infinite scattering length but has a bound state. Now, you know, if I go beyond this point, there's no two-body bound states, but bosons have n-body bound states, and in particular there's three-body bound states, even on the side where A is negative and there's no two-body bound state. But also those disappear. And I've indicated where they disappear. This is the lambda d bar star 3, where the last three-body bound state disappears. It's a bit to the right of this point. And then, so on, the scattering length sort of rises from minus infinity eventually towards 0, and then stays positive throughout, and near the 0, it's a linear behavior with a prefactor which actually can be determined precisely via numericals. And the point, what I will argue in the following, is that this point where the scattering length eventually goes through 0 and stays positive, that's the point where we go from a liquid ground state to a gaseous ground state. So the way the ultracold gases we love, they all sit sort of, if you wish, formally on this right branch, on this branch A positive, but of course in a way not this one, but some branch much farther to the left, but in a way we forget all these bound states because they are inaccessible kinematically. Okay, and the critical value for this de Boer parameter is 0.68, where sort of actually the van der Waals length, van der Waals length is only 86% of the van der Waals length. And so we have a picture where we say, okay, we can create liquid ground states, and for helium-4 we have it. When the de Boer parameter is between 0.37 and 0.68, it's a liquid. It has a finite density at 0 pressure. The density is actually set by the short distance scale, and you know the phase diagram quite well. And it has the triple point has disappeared. The critical point is still there. And now we want to go further. We want to crank up the 0 point energy even further and want to see maybe how can we go from here to there, or perhaps the other way around? Can we go from the gases to the liquids? This happens, and you get a ground state phase a finite temperature phase diagram, which looks very simple now. The ground state is a superfluid gas. It is separated from the normal gas by a continuous transition, indicated here as a dashed line. Actually behaves as T cubed at low temperatures. And eventually, of course, if you could imagine pressuring the system like mad and then making it a solid, but you will not get a liquid. That happens in an equilibrium situation. The only system in nature is spin-polarized hydrogen. Spin-polarized hydrogen has played a huge role in the early times of cold gases, laser cooling, and so on. That system has a de Boer parameter which is 0.74. So this lies to the right of this critical point. That's the only system in nature that really does that. But effectively, of course, we have it in ultracold gases because we can neglect all these bound states below, and then we get a phase diagram like this. So question is, as I mentioned, can we perhaps go from one to the other? Can we, in a way, go from a liquid superfluid to a gaseous superfluid, in a way, by going through 0 scattering length, perhaps. Now this can be worked out, essentially analytically by looking at what is called the effective potential. Do not confuse the effective potential with just putting into the Hamiltonian some mean field approximation. That's the effective potential after integrating out everything. That's a pretty complicated beast, but as a function for a Bose system, there's a complex field psi. If it's constant, the effective potential starts with minus chemical potential times pi squared, with which we can regulate the density. Then there is a quartic term, and then there's term 6th order, and so on. In principle, all higher order terms exist. What are the coefficients? Well, the coefficient of the quartic term is determined by two-body physics. So 2 particles in, 2 particles out. So that's determined by the scattering length. And that term, of course, I'm now interested in a situation where that term changes sign. If it's positive, I don't care about the 6th order term. And then you recover Gross-Pitayevsky theory as, in a way, the universal low energy theory for a dilute Bose gas. That's a point of view that was emphasized by Sachdev, and okay, there's lots of things I could say here, but for instance, that this chi here, this chi is the full scattering length, and it's not the Born approximation to the scattering length. And the way to go to prove this is to go to this effective potential and not just take the bare interaction. But now the question is, if this chi becomes negative, if the scattering length becomes negative, the Boer parameter is less than this critical value, we need a higher order term, and we hope for it's positive. Otherwise, we would have been in trouble. This coefficient D, which I've introduced up there, is called, or has been called, the three-body scattering hypervolume, and it was introduced in a paper by Shinatan in 2008. It's in a way analogous to the scattering length, but now at the three-body level. You have to determine the scattering of 3 bosons in, 3 bosons out, near 0 energy. And this problem with short-range interactions is still manageable. And the asymptotic behavior of the three-body wave function at large distances is 1 minus, 1 is just sort of the constant from the plane waves, if they are all very far apart, minus, and then it decays like sort of 1 over essentially distance between these particles, so-called hyperradius, to the 4th power, and therefore, of course, in the denominator, I need a quantity which has dimensions length to the 4th, centimeter to the 4th. That's the hyperradius. And in a way, quantitative calculations of this 3-body scattering hypervolume for short-range interactions like the ones I've shown have only been carried out in the last 2 years or so by Servas Kuckelmans and collaborators. And it turns out, luckily if you wish, that near the 0 of the scattering length, this d parameter is essentially van der Waals length to the 4th. I mean, well, there's a numerical factor here, so I've given the number here, which was determined by Servas and his collaborators. And then this gives rise to a 0 temperature phase diagram, which looks very simple. If I'm on the side where G is positive, so we have repulsive interactions between the bosons, things are very simple. Changing the chemical potential from negative to positive gives a continuous transition, which is described by Gross-Pitayevsky theory. If I let the scattering length go to 0, I reach this point here, which is a quantum tricritical point, because at this point, the 4th order term changes sign. But then the 6th order term saves me, and it's sort of the standard example which you can find in textbooks on statistical physics, for a tricritical point, a quantum tricritical point here, and you get a density of a liquid which at 0 pressure, so there's this points here on this line, describe a 0 pressure liquid whose density, so that there's a jump in the density from the vacuum to the liquid, but this jump goes to 0 if I approach this point. So it's very nice, but the question is, I mean, how does it evolve with finite temperature? And for instance, do we get what we naively expected? Perhaps, do we get a phase diagram like the one in helium-4? The answer is no. It's more subtle. That was worked out not by myself, but by Damson, actually last year. And was published only this year. The phase diagram, if you crank up the 0-point energy, you go from a helium-4 type phase diagram to something which is this, and only then you go to the phase diagram of the gases which I've shown. Namely, there is a now finite temperature tricritical point at a temperature which is set by the 0 pressure density n bar, and there's a phase diagram where at low temperatures you have a 1st order transition from a superfluid liquid to a normal gas. So this is 1st order, and this is a tricritical point, and then above you get a continuous transition from the superfluid to the normal system. Now, the ideal system I would like to apply this to is helium-2. Helium-2, not in the old sense of superfluid helium, but helium-2 with a nucleus which has 2 protons. That system would be ideal. That would actually have a phase diagram like this, and you can actually predict the density of this system. It would be a liquid. But the d proton is unfortunately not bound. That's an interesting story. Dyson has speculated about this, and life would be different if the sun would only last. Perhaps the speculation was the sun would only last for a few million years if the d proton would bound. But apparently this doesn't seem to be true. I've actually given a reference in the lecture notes on this story about what astrophysical implications the bound d proton has. Now the question is, can you see some liquid phases in gases? And the answer is, well, yeah, we can, in different systems so far. The first who actually sort of achieved this is Igor Ferrier-Barbu, who was at that time a postdoc in Tilman Pfau's group in Stuttgart, and now I think has a position at Institut d'Optique in Orsay. where actually in a dipolar gas of dysprosium with a large magnetic moment, you look at the expansion in a waveguide, and you look at the optical density as a function of expansion time, and then this system, if the dipolar interaction is strong enough, actually expands as a series of blobs, and these blobs themselves do not expand. So they are apparently a liquid phase, which comes from the attractive interactions of the dipoles sitting on top like this. And you can explain qualitatively this observation by saying that now we have finite scattering length, but finite dipolar interactions, and what stabilizes the liquid in this system is not what I called this three-body repulsion, but is the Li-Huang-Yang correction at finite scattering length, and the estimate gives a density 10 to the 14 per cubic centimeter. Actually, Igor Ferrier-Barbu estimated also whether three-body effects would be important here. They concluded no, they would give rise to densities even higher. So the question is, I mean, can one stabilize bosons as liquid phases with three-body repulsion? And there one has to, of course, we can easily always change scattering lengths from positive to negative. And usually the law is that, okay, if you have negative scattering length, unless we are in a trap, then it's unstable. Well, it depends, but in particular, if in a generic zero crossings of the scattering length, this three-body scattering hypervolume is not a real quantity as I've introduced so far, but is complex. And the complex value, this complex part of the imaginary part of D, is related essentially the so-called recombination length, which people have introduced in three-body decay. So there's a relation which was pointed out by, again, by Tan a few years ago. And actually, sort of the group of Lev Kajkovic, Shotan et al., and also the Servas-Kopkelmans have measured, for instance, in lithium-7, which has a zero crossing at, I think, 850 Gauss, a scattering length. The naive expectation, three-body losses vanish at zero scattering length, but they don't vanish. They have a finite value, and they estimated the corresponding recombination length. And interestingly, what they find is that the recombination length is around 4 L van der Waals. So you see, this is pretty close to, in a way, the fourth root of the real part I've calculated with the repulsion. And so what one wants to have to realize something like this is a situation where, in a way, the real part is large compared to the imaginary part, so losses are almost negligible, and the densities you get are not too high because sort of the real part is enhanced. If you see from this expression, if you make, you want to make this D, I mean, not too small, not of the order of the van der Waals length, but somehow I added that. And there is a suggestion by Dmitry Petrov a few years ago, which actually relies on having sort of two internal states, coupling them by a microwave field, and then the effective scattering length in the symmetric configuration actually can be tuned to 0 with the effective Rabi frequency and the parameter psi, which is related to the difference between these up-up and the up-down scattering lengths. And then you would get liquids stabilized by essentially three-body repulsion at some reasonable densities. So far as I know, this proposal has not been realized. One of the problems is that basically the theory also relies on assuming that A up is equal to A down. That's not, you don't have such a configuration, and I think it's not easy to realize that. So I'm pretty much over time, and I think I probably, I could say something about sort of n-body states, but I probably omit those, and perhaps at this point just switch the last slide. What I've shown in this, in a way, relatively general introduction is that both, essentially superfluidity and BC arise from a topological property of the many-body wave function. And if you have a system of bosons, as long as the interaction can be as strong as you wish, it always remains as a fluid. And that whether you have a gas or a liquid, this is the boundary is determined essentially by two-body physics, by vanishing scattering length. And in principle, and this is in a way the hope that eventually this will be realized also experimentally, for small negative scattering lengths, even in a uniform system, you may stabilize a liquid phase of bosons with repulsive three-body interactions. Okay, I think I end here, and thank you for your attention.